Okay, I wanted to start and kind of go over one of the common methods of integration that we use, which is integration by parts. We typically apply integration by parts when we have two functions multiplying each other. And I'll give, typically the way we write this is u dv equals uv minus the integral of v du. All right. And in these situations, typically the u and dv, there's two functions that tend to come together underneath the integrand. Okay, so this method of integration is relatively intuitively straightforward. If I look at these axes over here, so let's say I have on my y-axis I've called u, and on my x-axis I've called v. So basically this function I've plotted here basically says u is a function of v. Okay? And let's say we're computing the integral up to this point right here. Okay, so if I were to, I'll sort of with a hatched line here, show the area under the curve like that, that area would be simply u dv. Okay, that's what we're looking to solve for. Now, this point here is v. This point all the way up at the top of this function here is u. So I can look at this thing and say, well, if I look at the area bounded by u and v, it looks like I've got a square. So the total area of that square, area of square, equals uv. Now, if I were to say, what's the area between the curve and the y-axis, so this area, all right, if I were to say, what's the area between the curve and the y-axis, this would be v du, okay? So if I look at this, I can say that the area of the square, which is uv, has to be equal to the integral u dv. That's the area between the curve and the x-axis, plus the area between the curve and the y-axis. So integral v du, like that. That tells me the integral of u dv has to be equal to uv minus the integral of v du. Okay? Now, that's kind of the intuitive meaning behind it. It's important to have that. Typically, we said when we're using this approach, it's the case that under the integral, we have the product of two functions. And because we have the product of two functions, it's somewhat difficult to figure out which one is the u and which one is the dv. So as an example, what I'm going to do here today is x natural log x dx. Okay, that's the guy I'm going to do. Now, the way that I approach this problem, I have a way I was taught it, I guess, is the understanding which function to choose for the u substitution. And the order of selection that I learned basically was this: lipid, or as we were taught to remember it, large Italian people eat tortellini. That's how we learned it. And what it tells us is the first function that we would choose if we have it for the u value would be a logarithm. The second type of function we would choose if we have it is an inverse trig. So this would be something like arctan of x or inverse sine of x. A polynomial, so an x squared, that type of thing. An exponential, or a trig, meaning something like sine x. Okay, so those are our typical sort of ways of doing this. So let's take our example, x log x dx. Okay, so I'm going to say that this is equal to u v minus the integral of v du. So we have to choose u and we have to choose dv. Looking back at my order of my u substitution, Lipit, I see that I have a log and a polynomial. Because log is the first in the list, I'm going to choose the logarithmic function as my u substitution. So I'm going to say u equals log of x, and I'm going to say dv is equal to x dx. So what do I need to do? Now I need to take the derivative of the u. So du dx equals 1 over x, because that's the derivative of log. So now I know that du equals dx over x. Now for this guy, I've got to integrate both sides. So I have v equals 1/2 x squared. Okay? So I have everything I need. I'm going to need this guy, I'm going to need this guy, and I'm going to need this guy to be able to complete this thing. So uv is 1/2 x squared log x minus the integral of v du. Okay, so it looks like I have 1/2 x squared, that's my v, times dx over x. So I see that when I have x squared over x, that's just going to become x. So I'm going to simplify this guy and say I've got 1/2 x squared log x minus 1/2 times the integral of x dx. And I see that I've simplified that guy down pretty far at this point. So I get 1/2 x squared log of x minus 1/4 x squared, and then of course I'd have my constant of integration. All right, so just kind of a simple process for you guys to be able to remember to solve this type of problem. If I had something like, let's say, I don't know, x e to the x dx, and again I have to do my u substitution and my dv, I see that I've got an exponential and a polynomial. So if I go back in this particular case, log, inverse trig, polynomial. Polynomial is the first thing I come to, so I say that u would be x, that's the polynomial, and dv would be ex dx. If you follow that same approach, right, you would basically get the same type of answer that we did before, okay? And we could go through that relatively easily here in this particular case, and you guys can figure out how to do it. But the critical thing is understanding this Lipit idea, that this Lipit mnemonic, large Italian people eat tortellini, right? It's easy to remember that. If I look at that mnemonic, it tells me basically everything I need to know, because it tells me how to choose that u substitution. The tricky part about using something like integration by parts is to say that you may have to do the integration a couple of times, okay? You guys have in your homework, for instance, things like e to the x sine x dx, okay? When I get something like that, sometimes that needs to be, I need to apply the integration by parts idea a couple of times before I can get to a final answer. That's the only other tricky thing about it. If you understand this order of functions for that u substitution, then it becomes a relatively straightforward problem. All right, so I think you guys will be able to figure it out. It's just really comes down to knowing that, and knowing that occasionally when I have a problem like this one right here, the integral of e to the x sine x, I just have to do the problem a couple of times before I can get to a final solution.